Okay, so today we're just going to follow up, finish up yesterday's notes on graphing rational functions. So today I want to continue the thought of finding places on our graph paper where we're really not allowed to graph. We sometimes refer to these as points of discontinuity or lines of discontinuity in the case of vertical and horizontal asymptotes. So we're just going to add to what I gave you yesterday. More things to be on the lookout for before you start graphing the actual graph. So let's talk about what an oblique asymptote is and how to find it, and then we'll talk about this concept called a hole in a graph and how do we find those. So you will have an oblique asymptote, and you can just think of the word slant when you see the word oblique. It's going to be a line with some slope, slanted line. You will have an oblique asymptote if these two things are true. First of all, the numerator and the denominator are polynomial functions. And we're typically talking about binomial, trinomial. Poly means many, nomial means terms. So if the numerator and the denominator are polynomial functions, and there aren't any common factors, so that's another way of saying there's nothing that we can cancel between the top and the bottom of the fraction. So that has to be true, but not only that, it also has to be true that the numerator degree has to be one more, just one more, than the denominator. So we're talking about a situation where the numerator degree would be x cubed, or 3, and the denominator degree would be 2. Or maybe the numerator degree is 4, the denominator is 3. It's only got to be off by 1, and the numerator has to be higher by 1.
Only by 1.
Just by 1. Right. If this were 4, then I don't have an oblique asymptote because it's a difference of more than 1. Okay. So now that you know how to spot them, let's figure out how to actually know how to graph them. So here's a function, and I notice that I've got numerator, denominator that are both polynomial functions, or polynomials, and the degree of the numerator is 2, the denominator degree is 1, so it meets all of the qualifications for having an asymptote that we call oblique. So the way we find out exactly how to graph it is we use long division. We're going to divide the denominator into the numerator, and I've got it already set up for us. So just a quick review of how long division works. We always divide first term into first term. I'm going to divide 2x into 3x squared. So what that would look like, if we just come off to the side and do a little work, it's like saying 3x squared divided by 2x, and we simplify this. So what would that look like when we simplify? You see that it would be, I'm going to call this 3 over 2x, or maybe you think of it as 3x over 2, which is the same thing. So it would be 3 halves x. Everybody with me so far? Question?
How did you get the 3 x?
Well, just from 3 divided by 2. And when the x's, they're the same base, you just subtract exponents. 2 minus 1 is 1.
So that's what you would multiply to get the next.
Yeah, when you multiply 3 over 2 times 2, you're going to get 3. Because that's the next step. We take what we got when we divided, and we're going to take this and multiply by each of these. Here. All right, so 3 over 2x times 2x is just 3x squared. And then we also multiply 3 over 2x times negative 1, and that's minus 3 over 2x. Long division always involves subtraction. So when we subtract, the x squares go away, cancel. And when I do 0 plus 3 over 2x, I get 3 times x. We bring down the next term and we start the process all over again. I always divide first term into first term. All right, so this is a little more complicated than what we've seen in the past, but if you just do something off to the side, it might make it a little bit easier. It's like I'm dividing 3 over 2x by 2x. Well, first of all, what happens to the x's when we divide? What happens? They cancel. So I'm just going to treat these, I'm just going to mark these out because x over x is just 1. So now I'm back to that same old rule that comes up a lot. When you divide by 2, in this case, you need to change that into what? Multiplication by, which is 1/2. So instead of saying 3/2 divided by 2, it really means 3/2 times 1/2, which is what? 3/4. Okay, so we've discovered that 2x goes into 3/2 x 3/4. And we do that same thing, we multiply. 3/4 times 2 is 6/4, but that reduces to 3/2 x. And 3/4 times -1 is -3/4. We subtract. Now, at this point, save yourself some time. When you reach a point where division is no longer possible, and it's not possible any longer because when I get to this point, the x's are gone. 3/2 x minus 3/2 x is 0. This is just going to be a regular number. And can I divide 2x into any just regular number? No, I can't. So division at this point is over. The remainder is irrelevant. You don't need it. All we need is this, which is a linear equation. So I want to save you some time. I don't want you to think that you have to keep working this and come up with the actual remainder. When you get to the point where you can no longer divide, in this case, I can't divide 2x into just a regular number because this doesn't have a variable any longer. So my oblique asymptote is going to be the line y equals 3/2 x plus 3/4. It's just slope-intercept. And in just a minute, we're actually going to be graphing this function, and we'll put this oblique asymptote on, but I wanted to go ahead and show you how we get it before we get there. So, questions? Any questions on what we just did? So the big takeaway so far is you need to recognize when an oblique asymptote is going to happen based on the degree of the numerator being 1 more than the denominator. And these are polynomials where no canceling is possible. So you just jump into long division. We're done. Yeah, what we need is this. We don't need the remainder. We need the slope-intercept form for a line that we'll draw, which will serve as a slant asymptote. Okay, let's try another one. Yeah?
This is not calculated math, but can I switch to the C?
Sure, yeah. Okay, so I went ahead and set this up for us. I just went ahead and put some spacers in. These don't have any value. It's just so that we can line up the terms. So once again, I'm dividing first term into first term. And if I divide x cubed into x to the 4th, that goes x times. X to the 4th divided by x cubed is x. And now I multiply. X times x cubed is x to the 4th. X times 2 is 2x. Subtract. The x to the 4ths cancel. This really is no value. It's just in there as a space, so it's like bringing down 0, which is not needed. I will bring down the minus 2x squared, and you can go ahead and bring down 0 minus 2, which is negative 2x, and 1 minus 0, which is 1. But do you recognize now that we really can't divide anymore? Because x cubed is larger than x squared. You can't divide into something that's smaller. So I'm done. So my oblique asymptote in linear equation form is just going to be the line y equals x. That should look familiar. What's that look like?
On my parabola graphs.
Okay, y equals x. That's one of your parents, and it goes through the origin. Oh, I missed it.
Say a
Pretend
little bit.
it's a big origin, so just pretend it went through the origin. It's like that. So, long division helps us find the oblique asymptote, and I hope you understand when we have one. So now let's turn our attention to when do we have a hole in a graph? What's a hole? The book uses the fancy term point discontinuity, but I think if you see it, using the word hole is going to make sense. First thing I'm going to do, and you should always do this if possible, is factor. So the numerator can be factored because it's the difference between two squares. The denominator is prime. Here is how you will know if a hole in a graph exists. We're used to starting with the denominator to see if we have a vertical asymptote, and a vertical asymptote is a number that causes 0 in the denominator when we plug it in for x. So what is that number that causes 0 in the denominator? 4. Do you notice that that same number 4 also causes the numerator to become 0? That's the classic definition of a hole. It's a single number that not only causes the denominator to become 0, but it also does the numerator. It does both. One number that would cause both of these to become 0. So I'm going to have a hole in my graph where x equals 4. So let me just do a rough sketch. I don't have graph paper, but we could just draw a little xy plane here to illustrate what a hole looks like in our graph. Remember my last step on your notes, I always put in parentheses to simplify if possible. Well, last night it was never possible. Well, now it is. Do you see how I can cancel these? So something that really started out looking really complicated, that looked kind of ugly, you know what we're actually going to be graphing? We're going to graph the line y equals x plus 4. It's algebra 1. Y-intercept 4, slope of 1. We're just going to draw that line. So let's make some marks here and we'll draw the line. That's why I was saying I want to stress that when you can cancel, it makes graphing these so much easier. Okay, so since I canceled, I'm going to graph f of x or y equals x plus 4. So y-intercept 4, slope of 1, up 1, right 1, up 1, right 1, right 1. I'm making several dots so I can have something good to draw through. It's on graph paper. So you can just do a rough sketch. Here is y equals x plus 4. But can we use in this function, in the original, I know we've canceled out, but in the original, can I use 4 as an input? No, because if I do, I get an undefined situation. So if I can't use 4 as an input, that means a certain ordered pair can't be generated. What is f of 4 over here? So, in other words, if 4 can't be used as an input, the point 48 really doesn't even exist on this line. Because 4 is not allowed. Well, if the point 48 doesn't exist, right now I'm showing that it does, because I'm going right through it. 1, 2, 3, 4, and I'm going to say 48 is right there. Well, that means that if 4, 8 doesn't exist because 4 can't be used as an input, I should have a hole, and I can't erase my line, but you can. I should erase a little part where 4, 8 would be, and I'm going to draw a circle representing that the line's actually jumping over 4, 8, and then it's going to continue on after that. That is an example of what a hole looks like in a graph. I hope you understand why it has to be that way, because 4 can't be used as an input. Any questions? Okay, so let's apply what we've learned. Let's do this graph. So a lot of what we did last night is going to come into play again. We start by finding the 0, and we take the numerator, make it equal 0. That was pretty easy. X equals 0. We know our graph has to pass through the origin. Let's go down to step number 2. Let's find any asymptotes. We'll start with the vertical asymptote. So do I have a vertical asymptote? What is it?
-2.
X equals -2.
Sorry, X equals -2.
It's all right. -2 causes 0 in the denominator, so let's draw that vertical line. Okay, here's something new that you did not have to deal with last night. Do I have a horizontal asymptote?
Yeah.
Heard yes.
Yes.
What is it?
1.
How'd you get 1? It's y equals, since it's a horizontal line. How'd you get 1? You're right. How did you know it was 1? Just curious. Remember yesterday in your notes, I gave you 3 scenarios.
Remember in contacts.
Okay, and how did you know to use that? What about the degrees tell you to do that?
Degrees are equal.
They are the same. Remember in your notes yesterday, I said if the degrees are the same, and in this case they are, they're both 1, then you just make a fraction using the numbers in front. I call them the lead coefficients. And 1 over 1 is 1. So we're going to draw a horizontal line, y equals 1.
This being what, 3 graphs or 4 graphs?
It's actually still in 2 parts. That's a great question. By virtue of the fact that I cannot cross, these are like fences. If I have a graph, it cannot cross this way, and it cannot cross this way. And that's also true down here. So what it boils down to is, I'm going to have a graph section that's either up here or down here. Can't be both, because I can't cross this line. And on the right side of the vertical, it's got to be either up here or down here. And now we're going to do inputs and outputs to see exactly where. Okay, follow me? Everybody with me? Do I have to worry about a oblique asymptote? No, they're not 1 degree different, with numerator being higher. So don't even have to worry about the oblique. Do I have to worry about a hole? Is there a single number that causes both denominator and numerator to be 0? No, so there's no hole. So we're ready to do some inputs, outputs. So I'm going to start on the left side of this vertical line, x equals -2, and I'm going to start with inputting -3. So we're going back to our function, and if we let x be -3, we get -3 over -1, which ends up being +3. So the point -3, +3 is on the graph. Well, here's an example. I think I told you yesterday, depending on the function that you're given, it will determine how many inputs you have to do. I really don't need any more inputs after this, because I know that I've got to pass through this point. And I also know that this graph has to go up forever, because we always trace along a vertical asymptote. I can't go this way because I would stop. And the whole idea of a vertical asymptote is you approach either positive infinity or negative infinity. Well, I can't go to negative infinity, so I must be going all the way to positive infinity.
If it didn't have the horizontal asymptote, we could either go down or up.
Yeah, then I'd have to do some more testing. And that same thing is true for horizontal. I still have to pass through this point, but the only way I can go is to trace this horizontal asymptote toward negative infinity. So I'm really done with that piece. And I only had to do one input. It's when you have asymptotes, I think of them kind of as a way of pulling your line towards them. Because that's really the definition. We have to approach but never touch going to the left. Does that make sense? Everybody with me? Okay, so now let's try, we know what the left side of x equals -2 looks like. Let's try the right side using -1 as an input. Okay, so -1, that's going to give us -1 over +1, which is -1. So let's plot the point -1, -1. I actually have 2 points to draw through on this part because we know we got to pass through the origin. But the same idea applies. I'm going to pass through these points and trace the horizontal asymptote forever toward x equals +infinity. And then I'm going to trace all the way toward negative infinity down the y-axis. And we're done. Not bad, right?
Not bad.
You just have a little bit more to think about in the preparation part. I'm giving you poles to think about and oblique asymptotes. Yeah. Yes. And we're actually going to, if you didn't get this, we're going to do this again at the end. I didn't really count the points. I just started here and did up one, right one. So let's see, 1, 2, 3, 4, 1, 5. And you could use, of course, 0, 4, -1, 3. Another point. Okay, let's move on to letter B. Okay, first thing, find the zeros. So once again, we're going to let the numerator equal 0 and solve. 3x squared is -8. X squared is -8/3. At this point, I know I've got to do the square root of both sides, but I'm going to be doing the square root of a negative number. And when it comes to x-intercepts, this has to be a real number. And I don't get any real number solutions out of this. I get 2 imaginary solutions. So I do not have any x-intercepts. Interesting. My graph will never touch the x-axis. All right, let's jump into asymptotes. Let's start with the vertical. Vertical asymptotes are numbers plugged in for x to cause 0 in the denominator. So if you're not sure what that is, just let the denominator equal 0 and solve. 2x equals 1, x is 1/2. That's a vertical asymptote. Here's that one. Okay, do I have a horizontal asymptote?
No.
How do you know?
Because the numerator is bigger than the denominator.
Good call. The numerator degree is bigger than the denominator, so that means no horizontal.
But that's still
Okay.
If you can't ever touch the x-axis, wouldn't that technically still be your asymptote?
With what?
Wouldn't the x-axis, wouldn't that be technically the
No, it's not an asymptote. It's just that we're going to have a graph. Think of a hyperbola. Hyperbola is like 2 parabolas that open opposite each other. That's where we're headed. But no, the x-axis isn't a horizontal. So do you remember the oblique asymptote? We've already done this. Look back in your notes. We already found the oblique asymptote for this problem. And what it is? Can somebody tell me? You look back a few slides.
3 over 2x plus 3.
Okay, so I just saved us a little bit of time. I showed you how to find it, and now we're actually going to put it on our graph. So we're just going to graph, just like we've done in the past, the line y equals 3/2 x plus 3/4. So it starts with a y-intercept of 3/4. You can say that's right there. And then we count a slope, rise over run, 3 over 2. So up 3, right 2. Up 3, right 2. And do your best. I know you probably don't have a ruler, and that's okay. Just do your best to draw a straight line through those points.
Where exactly did you get the 3 halves?
We did it back in on this slide.
Oh, so you lose on additional time.
Yes. Yep. Okay, so now we're ready to do inputs, outputs, and the big question now is, am I going to have a graph part here above the slanted dotted to the left of the vertical dotted? Will it be in this area? Will it be in this little triangular region? Will it be over here? Will it be down here in this triangular region? So inputs and outputs will tell us exactly where it's going to be. So I'm going to start with an input of -1.
Can you use your
Oh, you can. We will. So what's the output? If you do input -1, 3 times -1 squared plus 8 over 2 times -1 minus 1, what do you get?
Isn't it positive 3? Not negative 3.
Oh yeah, I'm going to put -3. Thank you. Looks like 11/3, right?
Oh, that's fine.
-11/3. And as a mixed number, that would be -3 and 2/3. So -1, -3, and not quite to -4. So that's great information. I know I'm going to have something in this little triangular region. But let's get a little more specific. Let's try, well, Dalton mentioned, let's try 0. What do we get as an output or input 0? -8. So 0, -8 is on the graph. Okay, and then let's try another one. Let's do -2, just to be sure of what's happening here. Does it go up and higher before it approaches? Let's get exactly what happens. What do you get for output -2? Or all asymptotes are dotted. Yeah. Because they're not really part of the graph. It's really what we can't graph. You got -2 yet? -4? Everybody get -4? Just let x be -2. This is 12 plus 8 is 20 over -4 minus 1, which is -5. 20 divided by -5. -2, -4. Okay, so it looks like this is really going to be the highest point. So from here, I'm going to just trace the asymptotes. It's not a parabola because it doesn't have symmetry, but it's kind of parabolic. Good? Okay, well here's the deal. If you end up with a situation like this and there's a piece in this area, it's probably a good chance that the other piece is going to be in the upper triangular region. So let's keep doing some inputs. Input 1. It's the output. Chris, you got that? I can probably do it manually. It's 1 squared is 1, so it's 3 times 1 plus 8. 11 over 2 times 1. Yeah. 11. Okay, so 1, and I'm not going to change my units, I'm just going to put 11 up here.
It's almost about we're at 12.
Okay, I think we can finish this one. Okay, let's do one more. 2. You might have the output for 2. What? 20 over 3, which is 6 2/3. And I think that's going to be enough because I know where we're going this way. We're going up toward positive infinity. We've got to pass through this point, and then we're going to trace this one wherever along the oblique asymptote. Okay, so now we're ready for example C on these notes, and this will be the last example that we do. So here's our function, and I always like to go ahead and factor when factoring is possible. It's not exactly necessary, I think, until you get down to step number 3, but I'm just going to go ahead and factor everything. You're never wrong if you just go ahead and factor when possible at the very beginning. I think it's a good idea. Definitely factor and simplify before you start doing inputs, but in this particular problem, it's going to help us when we find the zeros and draw asymptotes to go ahead and look at the factored form of this. Okay, so finding the zeros, we always take the numerator and let it equal 0 and then solve. Okay, but in this particular case, we haven't seen this yet. We have factors that can be canceled. All right, so if we think about this function in factored form and then we cancel those matching factors, we're really only left with x plus 4 in the numerator. And if I take only x plus 4 and let it equal 0, I get x is negative 4. So that's going to be the x-intercept. Okay, going down to step number 2, drawing the asymptotes. Well, typically a vertical asymptote is a number that causes 0 in the denominator. Well, I started off having 4 as that number, but when I reduced, simplified, I actually do not have that to consider any longer, so there is no vertical asymptote. And there's no horizontal asymptote because the degree of the numerator is larger than the degree of the denominator. And there's no oblique asymptote. You might be thinking, well, what about this idea that degree 2, degree 1, it's 1 degree more. But remember, another consideration for an oblique asymptote is you cannot have any common factors. Okay, I'm just going to go back to our slide and remember, no common factors. Well, that is not the case here. We do have a common factor in x minus 4, so this cannot be an oblique asymptote. But what about a hole? Do we have a hole in the graph? Well, remember, a hole is a number that it plugs in for x, and it makes both numerator and denominator 0. So looking at the factored form makes that easy to see. If I did let x be 4, then I'm going to get 0 in both numerator and the denominator. Okay, a hole will always come from the number that would plug in for x in the common factors. Okay, that's always true. So I'm going to have a hole in the graph where x equals positive 4. All right, so let's go ahead and actually we don't really need to do inputs outputs unless you just want to, because in essence we're taking this original function and after simplifying it's going to be, we looked at this earlier, it's just going to be the line y or f of x equals x plus 4. So that's a y-intercept of 4, slope of 1, and we'll draw through that. So there is the line. Now don't forget, it's easy to forget. A lot of students will identify where the hole should be, but then when it comes to graphing, they actually forget to plug it in. So I should have a hole on this line where x equals 4. So there's a couple ways to think about this. I could go to x equals 4, which is here on the x-axis, and then just travel straight up, in this case, until I get to the line. And you are able to do this. You can take your eraser and just erase a little space right there. I'm not able to erase any part of the line. If I try to erase, it'll just delete the line. So I'm just going to do a little circle, but technically there should not be a line going through the circle. Okay, the line comes to where x is 4, it's the 0.48, it jumps over it, and then the line continues. So that's the graphic illustration of what a hole looks like. And I know we looked at it over here as well, just rough sketch form. Okay, so you might want to double check and make sure you have everything. You always want to, if you identify a hole, make sure you actually show it on your graph. And there's no need for a set of ordered pairs in this case because we just graphed a line using the y-intercept and the slope. Okay, so that wraps up part 2 of lesson 7.4. And I hope this helps. If you have any questions, let me know.